If I was to take this and put it, and we use this circuit, we use this circuit often. We were making digital clocks. This is not what I want. Starting at the So if I was to take one of these things that we looked at before, and I was to come up here and do this, and then I come over here, of course, I'm going to put more voltage in 7/10 of volt, so I'm going to come over and do this. Now, of course, what happens if I put DC on this thing? So if I come up here and put like 5 volts right here, then that's going to cause base current to flow, and that's going to cause my junction resistance to go down, right? I'm saying, everybody okay? Yes or no? Depending on how much base current we have, then that's going to cause this voltage right here to change. So if it's equal to approximately 0 volts, it means it's saturated. Basically, we say less than 1 volt, right? If VCC is equal to VC, if VC is equal to VCC, so right here, then we say it's cut off. If it's between cutoff and saturation, we say it's inactive. So what would happen on this one, and we see that my voice is an AC signal. So what would happen on this one if I came over here and put AC on this one? So I get AC out. Right there, let's say I'm putting 5 volts here, minus 5 volts there. What would I get on my output? Well, here comes plus. Plus comes over here. That would put a plus here. That would put a plus here. This is an NPN transistor. I got a plus here. I got a 0 here. The transistor is cut on. So the output would drop down. So when this goes up, this right here would go down. Now how much, I don't know. What would happen during the negative alternation? So this would be minus 5. This would be plus. So I got a plus on my emitter. I got a minus on my base. So what would happen? It would cut off. So this would be, when it's cut off, it drops the voltage. So what I would only do is I only get half of the alternation. By the way, we've used this circuit to convert 60 cycle into a digital pulse. So we made a digital clock. And Alabama Power 60 hertz is nice, right? You understand that? So we ran it through one of these guys right here, did a little work on it, saturated it. So it saturated real fast. So we ended up with just like this. When it's saturated, we never got to peak. We fed that into some dividers, divided it by 60, came up with 1 cycle per second, ran that into some counters, and set up and designed and actually built the digital. It still might be around here. So this would work awful. I could not use this to amplify my voice. Y'all understand that? Because it would do what? It would pass one-sided block rate. So it means I can't start off with the base going negative. By the way, normally we would come up here and do this. Now why would I do that? Why would I put that diode in? Huh? Well, it's not a zinger, it's a diode. It's not a regulator. So when this goes negative, it's going to forward bias it, and the entire voltage will be dropped across that resistor except for negative 7/10 volt. So on transistors, the base junction is not designed to be reversed. The base emitter junction is not designed to be reverse biased. So on the 3904, if I look at the data sheet on the 3904, which is the one we use most often, it says the breakover voltage collects the base to emitter, the reverse bias voltage, so the reverse bias voltage, base to emitter, is only what? So here's base to emitter, reverse bias is only what? You know, see what that says? 6 volts. So it means if I put more than negative 6 volts on my base, and I've got my emitter connected to ground, I could break that sucker over in the reverse direction, and there goes my transistor. So what the diode does, it prevents that from ever happening, right? So when this thing, and you'll see this a lot on saturated switches, especially working with AC. So if this goes negative 5, that forward biases this diode, so I'm only putting a negative 7/10 of a volt on my base. So this protects the diode. When it goes positive, this is reverse bias, and it puts a positive on the base and turns the transistor on. But it still wouldn't do AC. It would still clip off the negative alternation, right? Y'all understand that? So what am I going to do? How am I going to get this thing to pass AC? First thing, transistors don't do well with AC. They do really well with DC. They do very poor with AC. So what I could do is I could come up here and go ahead and put my, if somehow I could put my base at 2 volts DC, and then bring AC in there and allow it to add to and subtract from that, and we'll do okay. That makes sense? So somehow we're going to have to bias this thing, and the most popular way is what can I use to set voltage? Yeah, but you're not going to see any, well, you might see some potentiometers. So what is a potentiometer? It's a variable voltage divider. So I can come up here, and I can put a resistor right here. Say it's 100K. And then I can come down here, and I can put a 10K. And then I could hit my base right there. So what's the base setting at? Let's say I've got plus 20 volts up here. What would be the voltage on the base? The voltage on the base. So if I call this R1, I'm going to call this R2. Everything is relative to circuit common. So it's going to be the voltage drop across R2 is going to set the base voltage. So what would be the base voltage? Well, you're saying this guy here drops no voltage, this is K. This guy drops all the voltage. It's a voltage divider. So the sums of the voltage drops in the series circuit have to equal to the applied voltage. So I would say, okay, VR2 would be equal to 10, and I can drop the K. Why can I drop the K? It's on the top and the bottom, divided by 110K. And then I can multiply that by 20, and that would give me the voltage. So look, that voltage divider formula is a really neat formula because you can do the math with one formula. You could add them together. You could divide that by 20. You could take 20 into 20. You could take that and multiply it by the 10K to get the same answer. So what would be my voltage on the emitter? I mean, on the button. Okay, now it looks like I can bring AC into this thing, and my positive alternation would add to the 1.8, and my negative alternation would subtract. Does that make sense? So over here I have this circuit set up, just as though I don't have a transistor up here. Let me see if I can get a little closer. No, I'm sorry. Here, to show y'all this, what I have to make the math, here I have a brown, black, red. Here I have a brown, black, red. And I've got 5 volts connected to it with a voltage divider. So let me draw the circuit. Oops. So this is the circuit I have up here. So this is a 1K. This is a 1K. Then I'm putting plus 5 volts over there. And I'm going to measure right here. So what voltage should that measure? Got to drop 5 volts. Resistors in the series circuit drops the same size resistors in the series circuit drops the same voltage. I got to drop 5 volts. So how much does each one of those resistors drop? Shouldn't have to use your calculator on this guy. 2 resistors the same size. They're going to drop the same voltage in a series circuit. That means I should measure about 2.5 volts up there. That's something y'all should know, guys. So 2.5, they're the same size. 2.5 plus 2.5 is 5 volts, right? Okay. So here's my meter. Let me bring my meter up here to turn on power. And let's see if I start getting through that. Yeah. Here's my red lead. So we have 5.05, so I'm going to measure it here. It's measuring. Oh, okay. I don't know what it is. So 2.5. So what I've got is I've got an AC signal right here. They both use the same common. What's going to happen when I put my AC signal center those two? So what I'm going to do is I'm going to come up here. Oh, so what I'm going to do is I'm going to take an AC signal and I'm going to bring it in right there. What's going to happen? And all we're going to do is measure this with a voltmeter. We're not going to look at it with a scope. We're going to measure it with a voltmeter. Not yet. What we're trying to do is, what I want to do is I want to come up here and I want to bring an AC signal into here. And then what's going to happen if I come over here and do this, when this goes up, transistor turns on more, which is small, which would cause the output to go down. And then when it goes up, I want it to do this. And what I'm trying to do, that would mean I'm going to try to bring an AC signal directly into the base and let a very small AC signal and let it either add to the bias or subtract from the bias. So now if I've got a voltage there, if it goes positive, so if this is 1 volt, if this is 1 volt peak peak, and what would happen is that when it goes up, that's going to be voltage sources basically in series, and they would add. Then when it comes down, 500 millivolts down, then it would go from what? So that would be 1.8 plus 0.5, or it's going to be 1.8 minus 0.5. That's what I think is going to happen, but it's not. Because what we need to understand, the difference, what an AC source sees a DC source as, and what a DC source sees an AC source. So what I'm going to do is I'm going to switch back over to my camera. And right now when I measure in the center, it measures 2.5 volts. I'm going to bring this AC source in, and I'm going to put it there. So now it measures what? Okay. I'm going to take the AC source out, and it goes back up to 2.5 volts. Everybody understand that? It drops down to 0. When I don't add it in, and what I'm going to do now is I'm going to come over and take my common for my circuit out, and I'm going to use this AC signal. This is my common. This is an AC signal. I'm going to hook it up to the common side. So this still shows 5 volts. This shows 2.5. This shows 0. So y'all understand what I'm doing? So if I was to take So what happens is when I put this AC source, this right here drops to 0, which means this guy right here is dropping 5 volts. So basically what I did when I put that AC source in there, I basically shorted out that resistor. So that means that AC source is acting just like a common. When I come over here and take the common away and replace it with an AC source, this right here still measures 2.5 volts. So it's seeing the AC source as a common. So this is one thing that's very, very important. A DC source sees an AC source as a short circuit. an AC source sees a DC source as a short circuit. It'll fly through there like it's not even there. Y'all see what I'm saying? Yes or no? So my meter's over here connected to circuit common. I put my AC source right there, and that right there measures 2.5 volts. I put it right there, it measures 0. So what I did is what I did, it's just like me doing that right there. Just like when we're doing that right there. So that means I cannot bring an AC source into this because it would go to 0, and the amplifier would not work. So I need something that blocks DC and passes AC. That would let AC come into a DC circuit. Huh? What electronic device do we have that blocks DC and passes AC? That's the measurement equipment. I'm trying to come up with a component that I can put right here that keeps the 1.8 volts in and allow me to couple an AC signal into this. I need an electronic component, not a piece of test equipment. I need an electronic component that blocks DC and passes AC. So I've got a setting on my scope right here called AC. It blocks DC and passes AC. Anybody here had AC? So what does this guy do right here? So I come over here, I've got this device right here. Okay, I got that device right there. Its frequency, its resistance is set. It's called XOC. It's 1/2 pi LC. DC has 0 frequency. It has infinite impedance. A capacitor blocks DC. So that's what we're doing on our oscilloscope. In fact, I think I even drew this. So this goes into the amplifier of my oscilloscope. I put the switch down here. It goes through a capacitor. And then I put the switch up here, it goes directly in. So this is direct couple, this is AC. So when I put that sucker on AC, all you're doing is putting a capacitor in series. That's all you're doing. It blocks the DC and passes the what? The AC. So what that means is, if I have this capacitor right here, here I'll use the oscilloscope. My amplitude might be too hard. But I'm going to come over here and put this capacitor right here. Put my ground like that. I've got the minus pointing toward the AC. Both sides. I've got the positive pointing toward the DC. Now I'm going to come over here and put this. I'll keep doing that, guys. I don't need to. Okay, so I got AC. Let's prove it. First let's measure it. Let's see if I'm overriding my training. Five volts between my two. Of course, it's another. I got a bad connection. So here's 0 volts, if I can keep it working. Here's 0 volts right here. Here's my AC signal coming through my capacitor. So what I'm doing, I bring it to the capacitor, and it's actually doing what? Adding and doing what? Subtracting from the DC. So how did I do that? Well, I brought it in through a what? A capacitor. It blocked the DC, kept my 2.5 volts there. But when I measure it with a meter, even though it's got that signal on there, it's still going to measure, if I don't mess it up, it's still going to measure 2.5 volts. That's it. I got too much to see. One of my resistors keeps opening. Yeah, one of my resistors keeps opening. But what we can do is we can measure the 2.5 volts because your meter is going to see that AC is going down the center, right? You understand what we're saying? So what we have the ability to do now is I can come over here on this amplifier. I know it's almost time to go, okay. And I can bring this into a capacitor, and then I can bring AC in over here, and then this AC is going to add, when it goes positive, it's going to add to the base voltage. When it goes negative, it's going to subtract. And then what I'll get out over here right now, if this is 20 volts, depending on the size of the transistor on the gain, I'll get, if this is 0 volts, then I'll get a signal on the output that looks like this, according to the gain. We'll figure out how to do the gain before long. So, but it's going to be riding on DC. What would I do? So, transistor amplifiers are amplifying DC. We make it appear they're amplifying by AC by coupling, right? So on this one, I'm using a capacitor to let the AC signal in, keep the DC bias there. But I want to do the same thing over here, because this is going to be riding on DC too. So what we'll do over here is we'll come over here and put another capacitor over here, which will block this voltage right here, right? Y'all understand that? And allow us to get AC out. These are called coupling capacitors, but we got one more thing to do. We demonstrated this the other day. This guy here, the beta would change the temperature. And we wouldn't want that to happen on our stereo. By the way, this is called voltage divider to bias, and this is what we're getting in. You can see how I got this name, voltage divider bias, because we're going to bias the base up to a positive voltage or negative voltage for P and P. And then our AC signal is going to add to or subtract from that. And hopefully, if we design it correctly, it will not saturate and it will not cut off. We'll talk about that too in the next class. So you have a good weekend, guys. I think both Alabama and Auburn are off this week, aren't they? Yeah, they are, both of them. They both got bye weeks. Maybe by this weekend we'll see who the president is. Yeah. Yeah. Huh? Wow, it didn't have anything on it? I'll look.
Station Dennis, that voice all that.
It's loud. You don't have it. Feel like loud meter of the loud. Wow, that's not hard.
Oh.